one of the central ideas in the quantum mechanics is that a particle can evolve through like multiple possible paths and simultaneously, while the observable outcomes determined by the probability amplitudes rather than like the deterministic trajectories. And if we understand how these amplitudes propagate, interfere, or like eventually it can produce the miserable results in like, and these are all fundamental to the areas such as this whole quantum field, this quantum information theory, and the more theoretical physics. Okay, so after doing research in all these concepts, I developed a computational framework of the Quantum Galton Board to just investigate the wave function evolution, and the photon path propagation, the interference effects, and let's say the measurements, of course, the measurements, dynamics within a discrete lattice model. Sure. This project consists of the four components. First is an interactive visualization that just illustrates the photon path propagation through a branching lattice, what we call the Galton board. And then secondly, there's a numerical simulation of the probability amplitude evolution. Then in the number three, we've got an animation of the wave function, dynamics, and the interference. And in the number four, well, finally, we've got a measurement model that just connects the wave function evolution to the observable detection outcomes. So, if we just let's start with the Galton board. So we know, let's just say what is a Galton board. Apparently, Galton board is like it's a board game in the and it was used to play in the old Japan. What it is to do is that it's just a board and with differentiating paths, and a ball was dropped from the top. Apparently, and there is points in at the bottom of the board, 150, maybe 30, 20, just like dots. And the ball was dropped from the top, so the ball would just land following any of the path at a random outcome. And yeah, just like that. So, as you can see, here's a board. It just visualizes how the photon can propagate through a branching lattice structure. Here we go. I just added one photon. So you see, each of the photon begins from a single source, and it just traverses a sequence of the possible pathways through the network. If we just add some more photons in there, see, here we can see, although each individual trajectory appears in random, and the collective patterns we're getting in here, they are emergent as like more photons move through the lattice. And now you can see, in some of the photons, the path just accumulates together. This behavior reflects an important idea in the statistical and the quantum mechanics. It's called the complex distributions can arise from like many simple probabilistic events. Now, so this visualization just shows us the concept foundation for like the conceptual simulations that just follow where the probability amplitudes and the interference effects and the measurements are modeled numerically there. Anyways, so after this interactive visualization, I just extended my project into a series of computational models to investigate the wave function evolution, number one, then the interference phenomena, and then the quantum-inspired transport processes. So, first we're going to talk about the distribution simulation, what it does. Apparently, this simulation models a quantum Galton board a branching lattice that's just inspired by the beam splitter networks using the quantum optics, rather than just tracking like a classical particle. What it does is this model this model just propagates the probability amplitudes through like multiple possible paths, as you can see right in here. At each of the layer, a beam splitter transformation distributes the photon's probability amplitude between two possible directions, which is allowing the wave function to like just evolve through the lattice. So after propagating through the full network, these amplitudes are like totally converted into probabilities using the bond rule, which you call. And this bond rule, what it does, it just provides the likelihood of detecting the photon at the different output stations, different output positions. And so this probability distribution just represents the collective contribution of like all the possible photon paths through the lattice to the system. And instead of like following a single trajectory, the simulation just considers the superposition of multiple multiple paths. And an essential feature, this considers an essential feature of the quantum systems. Next up, we're going to just move on to our next one. So in this simulation, I extend the Quantum Galton Board framework to just like visualize the evolution of a photon's probability distribution. And as you can see, as it's going to propagate through the lattice. And so apparently what this one does, this system just begins with a localized photon state. Let it appear. There we are. It just begins with the localized photon state. Right at the top, it was there. At each one of the layer, a beam splitter transformation that just distributes the probability amplitude into multiple possible paths, which allows the wave function to evolve through the network. And rather than just observing only the final detection probabilities, so this animation just captures the whole propagation breakthrough. As like the photon explores the multiple paths simultaneously, the probability distribution just spreads throughout the lattice. And it just reveals how complex its statistical structures emerge from like repeated evolution that again and again and again as it just evolves. And so apparently by just combining the whole numerical simulation with the real-time visualization, it just kind of helps bridge the quantum mechanical concepts into a observational quantum computational behavior. There we are. And another thing here, each of the layer represents another stage in the wave function propagation, where like the probability amplitudes, they just continue to branch into like multiple possible paths rather than just tracking a single trajectory. Next up, we're going to go for our number 3. Apparently, what this one does, this just the whole background distribution. It just represents the evolving probability landscape of the photon's wave function as it's going to propagate through the lattice now. So, as you can see, wait for it to appear. There we are. So, rather than just following like a single trajectory, the photon is described by a probability amplitude distributed across the many paths that are probable outcomes. Now, after the wave function evolution is finished, a measurement is performed by sampling from the final probability distribution. Here you can see it in the calculations that I conducted right around in here. Just give me a sec. There we are. So as you can see, this highlighted path represents a single detection outcome. selected from like all the available possibilities. And apparently, what this does is this illustrates the whole relationship in between the wave function evolution and the measurement. And this happens when, right at that time, at the specific time, when a distributed quantum state gives rise to a specific observed result. That's all.